Okay, the recording has begun, so we are going to get going. So, hello everyone, we are team E55. We've been working on developing an augmented reality application to streamline and improve substation inspections for We Energies. So my name is Jeremy Horkey. I was one of the hardware managers for this project.
My name is Meg Helskamp. I worked on software development.
Hi, I'm Robert Kondev, and I worked on hardware management.
Hi, I'm Brendan Quinnett, and I worked on software development.
Hi there, I'm Russell Redding. I also worked on software development.
And then in addition to the five of us, we were also assisted by Joshua Hayes and Logan Smith, two industrial design students at the Milwaukee Institute of Art and Design. Our faculty advisor was Dr. Chandana Tama, and our two primary industry sponsor contacts were Mr. David Nestler and Mr. Paul Gogan. So we're going to start with the goals of the system and what we had come to agreement with the sponsors of what we are going to take care of for this project. So as we said, We Energies has requested us to develop an augmented reality application that will allow substation inspectors to work hands-free on a more intuitive system that automates inspection processes. What this means is that we needed to create systems that would integrate and automatically upload any collected inspection data to Cascade. We needed some system to easily check inspectors in and out of substations. We wanted to provide inspectors with additional reference materials such as device schematics and user manuals. We needed to update the GUI of the system, and we needed to create a secure hardware storage method. We wanted to give the inspectors the ability to switch between a normal camera feed and an infrared camera feed. And finally, we needed to create some system that will allow our system named Where to automatically recognize devices and pull up the appropriate form. So knowing all that, we came up with 8 tasks to develop this system. The first one is creating a docking app that will interface with Cascade and just serve as the primary hub for all inspectors. We also updated the GUI of our project and created a more secure housing for all of the hardware that we have. As for the check-in system, we decided to use RFID, radio frequency identification tags. We also wanted to create an alerts database for each device. We also wanted to create helper functions such as the device schematics and user manual. In order to recognize devices, we implemented a QR code scanner. We wanted to implement a system to record the inspections so that they could be watched back at a later date. And finally, we implemented the IR cameras to live stream the IR feed to the HoloLens. Rob, you're muted.
Sorry about that, it wouldn't let me unmute. So before we go into more detail about each aspect of the project, I'm going to talk about a little background first. So our project started as a continuation of a prior senior design project. So we wanted to go over some elements that we took from their project, some that we had to discard and modify, things like that. We're also going to talk about some previous designs that use augmented reality and how it led to our final MIAD design, and go over some costs of the system. So there were 3 main components that we wanted to take away from last year's project. The main one was the graphical user interface, the GUI. That included the pointer for the HoloLens, head tracking, things like that. We basically were able to take that and implement it into our project with no problems. The other two segments, the IR camera and the 3D scan, those had to be modified to kind of fit our need. From the previous project, the IR camera could only take in preloaded images onto the HoloLens. And we wanted to make sure that an inspector could switch to an IR feed at any given moment without having to plug video in at a later date. The second thing that the previous group had was something that they called a 3D scan, which used a GPS and image recognition to try to identify different components in a substation. Our group deemed that that was a very clunky way, a very unreliable way to identify which piece of equipment was what. So we decided to implement a QR scanner. Not only would it be relatively faster and easier to implement, but it would also be easier to upgrade in the long term if new equipment gets brought into different substations. So there are a few companies, like I mentioned earlier, that are currently looking into augmented reality development. One in particular, the photo on the left has Manitoba Hydro's implementation that uses augmented reality glasses alongside a hard hat. That sort of led to influence our final design in a way with MyEd. Other companies like VGIS and Duke Energy have also been using the Microsoft HoloLens in particular in different ways of implementing industrial processes, things like that.
So here's a diagram of the flow throughout the system. So when an inspector arrives on their site, they'll activate the Wear system and then check in using an RFID tag to be able to send a text message to get approval. Once they have approval to enter the substation, they have two components that they can utilize during the inspection. The first is an IR feed, and the second one is the QR scanner. When an inspector scans one of the equipments using the QR scanner, it'll generate a report that they can start to fill out. And once they end their inspection, they can return back to their office and using the docking system, grab the report data and then import it into Cascade.
So one of the advantages of being a Marquette senior design team is we had the opportunity to work with two industrial design students from the Milwaukee Institute of Art and Design. So we met with them at the beginning of this semester, and we had two goals for what we wanted help with for our project. So the first one is the hard hat HoloLens, as well as the IR camera integration. Also, do you want to? So this is what the final model looks like. So the HoloLens is able to coexist with the existing We Energies hard hat by using the system where the HoloLens clips onto the hard hat using like those two orange pieces that you can see in the top left corner. And then the IR camera is put on using like the band on the hard hat. And we decided to choose that location because we wanted the view to be the least disorienting for the inspectors. The next one was the hardware storage piece. So if you notice the belt in the bottom right corner, that is actually a piece that exists. The rest are just like 3D models that we have. And the belt is used to store our RFID scanners as well as the Raspberry Pis. And the Raspberry Pis and all the rest of the hardware components will be stored in those boxes that you see above.
Okay, so the next is the cost of the entire system. So the three main components to the system are actually the Microsoft HoloLens itself, the FLIR C2 camera, and the two Raspberry Pis that are needed. So overall, this entire system costs about $3,900 per inspector with its current with the current prices. except this should go down because the FLIR C2 camera is actually an out-of-date model, and newer models actually only cost a couple $100 and can be implemented quite easily. So with this cost for each inspector, with all of the QR stickers that are needed and the RFID tags, for all of the substations, it would cost about $560 to implement the QR codes and the RFID tags. And this comes to approximately $1.12 per substation, and is a very cheap task to add to more substations. And while this system is actually about $1,500 more than their current system of the laptops, it actually ends up paying for itself more than enough just by the automation that it really brings.
All right, so next we are going to move on to more specific details of how the WEAR system works. We are going to start with the RFID check-in system. So what we are doing is we have attached a RFID scanner. Russell, if you can advance the slide. Thank you. So we've attached an RFID scanner to one of the two Raspberry Pis and then written 4 scripts to operate it. One of the scripts generates a user ID document for the Pi and the WEAR unit as a whole. One manages the RFID tag database, and 2 are used to check in and out with the tags. So the scripts use a service called Twilio to send SMS messages to a specified phone number whenever a registered tag is scanned. The proposed infrastructure for this system is to include 1 registered tag per substation. So now, Russell, if you can go to the next slide, here's a demonstration of how this works. So those blue chips are the RFID tags. That is the Raspberry Pi with attached scanner. And this is the battery pack that will be powering both Raspberry Pis and also an additional battery for the HoloLens. So to create the user identification, they need to fill out 5 fields. It is the inspector's name, a Twilio account ID and authorization token, and then 2 phone numbers, one to send messages and one to receive messages. Once this has all been set up and there are tags, the tag database has been loaded onto the Pi, whenever the inspectors scan a RFID tag, it will send a message saying this person is checked in, assuming they're running the check-in program, which will be part of the WEAR application. And if they want to check out, they'll just run the check out option and do the same thing. So this is an example of the text messages that the RF scanner will send.
Okay. So the main challenge for implementing the IR camera feed is that there's no actual way to plug a camera into a HoloLens. The port that's in the HoloLens is only capable of charging and small file transfers. So if this wanted to be done, it would have to be done wirelessly. And so the way that we implemented that was using the same Raspberry Pi that Jeremy mentioned earlier. It would run a Linux package called Motion to set up a video stream or video server of the feed of the IR camera onto an IP network. From there, our Unity application would pull that data from the server and basically stream it to the user on our interface. So if you go to the next slide, we have a quick demo. The way to start the Motion script is using a bash script called motion.on. This sets up the Motion server. So then once you're connected to the same network as the Raspberry Pi, you can actually see the IR stream directly onto the GUI of our application. So we're going to start the test on an emulator here. We're going to go from our main menu here to the IR camera feed. This is something the inspector can do. And then they would see a live feed of the IR camera. So this is a pre-recorded video, obviously, but you can see that you're able to stream exactly what the camera sees onto our Unity application. From there, there's a second bash script that'll come up shortly that allows us to turn the server off when not in use. This is going to save processing power in the long term for inspectors, especially in warmer weather when the CPU is going to be running much hotter. So here we're going to have a demo now that the server is turned off, what the inspector will see when trying to run the IR camera feed. So we're going to run the test feed. Oh.
Sorry, do you want me to go to the end of the video again, or?
Just go straight to that. Basically, it'll show a grayed out box that will let the inspector know that there might be a malfunction with the camera, maybe it was unplugged in the process, and that the feed is basically cut off from the server, or the server is off. Yeah.
Okay, so the next feature is actually the QR scanner. And with this, what you can do is from the main menu, you can actually go straight to the QR scanner, which has its own scene. And this will start the scripts. So the Microsoft HoloLens uses its webcam to actually search for QR codes. And this is actually done using spatial mapping to determine which QR code and get the ID of it. And then, so when the QR code is scanned, it actually will bring up a form for you to fill out. And then once you click on the form, once you click on the fields in the form, then it's actually voice command. So what you do is when you click onto the field, you say the words enter text, and then you can say whatever text you want to input it into the field, and then you either have the option to hit submit or to exit out. If you exit out, it just exits out of the entire form, and if you hit submit, it'll actually put all those fields into a CSV currently. So from there, it can actually be implemented, like just pushed straight onto the Cascade database, and it helps for automation. So here's just a little demo of it, run through the emulator. Sadly, due to some bad timing, I had to show this on the HoloLens emulator, and the test inspection button will not actually be there in the real in the actual application. That was just there for testing purposes and to show you that the forms can pull up. And like the emulator is just supposed to show you that the box is there and that the QR code scanner should be working.
All right, so the docking application was created to interface and be the middleman between the HoloLens and the Cascade database. It also provides status for the entire system, and this is like the entry point for an inspector to see how the whole system is operating. It was built in Node.js, and it used Electron, which is like Chrome in a box, as the platform, and then React.js was used for the graphical user interface. And then I can pull up the demo right now. So here's the login page. The inspector can enter their credentials and hit login. And they'll be greeted with the status page. The status page contains three components, the HoloLens, work orders, and Cascade, and gives them up-to-date information on each component. If they navigate over to the navigation bar, there are two other pages. The work order page allows the inspector to add and remove work orders. I can give it a demo. I'll use. Once they've filled out these areas, they can hit the save work order, and this will append the table with the new information. If they want to remove a work order, they can also go to the remove work order module, hit remove, close the module, and now the work order is removed from the table. The final page is the HoloSync page, which facilitates the actual grabbing the reports from the HoloLens and then creates the .csv file for them.
Okay, so the last challenge would be from taking the data to the HoloLens to the docking application and then outputting the file. So over the course of the year, we have been in communication with DNV-GL, who runs Cascade. And they said the best way to communicate with their databases would be through a CSV file, otherwise known as an Excel file. Right now, the HoloLens will be exporting an XML file. And so what this does is it reads in the XML file from the HoloLens, parses and stores the data from the file, and then converts the data to the CSV file. So if you notice on the left side of your screen, that is me testing the code, seeing that the file has been written, and then exporting some sample data to an Excel file. Right now, it is a JavaScript-based application and is using a DOM parser.
Of course, throughout all of our development, we also created tests to validate that each operation is operating correctly. So we handled all of this through experimental verification. Our experimental verification looked similar to this table. So this is an example of the docking application running the executable. Each test is going to be divided into some section. So this is for launch. And then each test is given a test number, along with a description of what each general overview of what each test should do, the expected results of the test, and then pass or fail, handling the condition, whether if it worked or not. This helped us track and record the different issues that we're faced with throughout all of the development, as well as the stuff that we should return to when we had the opportunity to.
So in terms of testing the check-in system, everything with the check-in system does work as we expected it to. Unfortunately, just due to limitations on who was available to connect hardware together, we have not yet been able to integrate the check-in with the rest of the system. However, all it needs to do is be implemented within the primary Unity application, which will start up bash scripts on the Raspberry Pis. So it's not particularly complex to set up, but it still needs to happen as soon as the Pi can be connected.
So with the QR scanner, we too ran into some problems. So with the QR scanner, as shown in the demo, it does run without any errors. It can be downloaded and run on the emulator, and the function for the forms all work properly. However, due to a poorly timed expiration of our security certificate, we were unable to actually put it onto the HoloLens itself and test it out that way. And while this is a fixable problem in the future, it would just take some time that we sadly do not have.
So we wanted to break our camera testing into 3 separate sections. The most important was to find a way to implement the feed of the camera onto a server that can then be accessed later on. Again, this was done using motion, and it was proven successful. From there, we ran through a few different implementations on how to actually view that web stream onto the Unity emulator, 2 of which failed, which led to our final design choice of creating a custom web stream that would extract the data from a web server and implement it to the user on the user interface. Our final testing would be to implement it onto the HoloLens. Like Brendan mentioned earlier, we weren't able to actually upload the application directly onto the HoloLens. So that part of the testing remains untested, but with the success of the emulator, it's a good sign that it would work once implemented.
And in terms of generating and parsing the CSV and XML documents, I decided to break in and test each part individually, such as can I create an XML document? Can I write to it? Right now, everything functions as it should, except for being able to open an XML document from an external file. We are looking into how we would do that, and we have an idea, but currently it does not work as of this moment. But, you know, as any year-long project, we as a team have come up with like some ideas on how we would like to continue this project due to some unforeseen circumstances which disallowed us from completing all of our planned tasks. So currently the device alerts, helper functions, and the inspection recordings have not been implemented, but we have allocated space for them in our system design. Our individual components all work successfully on their own, but they need to be integrated into one complete system and then tested as a system. One thing that we found really helpful as a senior design team is that we were able to meet with a member of the team from the year before us and kind of transition the project. So to handle that in the future, we have compiled a project legacy documentation for any parties that would be interested in developing our system in the future. Does anyone have any questions?
If you do have any questions, feel free to just type them in the chat. I'm keeping an eye on that, or if no one's talking, just feel free to yell it out. Oh, so that's a very good question. The question, if anyone hasn't seen it, is does the system need Wi-Fi at a substation to work? So what we are doing for this is one of the Raspberry Pis is actually equipped with a 3G, 4G LTE shield with an installed SIM card. We're actually going to be using that system as a Wi-Fi hotspot. So the system does not need Wi-Fi at each substation, but it will require a cell connection. All right, so the next question is, are there any security concerns that we identified and addressed? I will also ask Rob to answer a little bit more on this, but from my perspective, the only security concerns that we may have are due to the fact that we are setting up a server on one of the Pis, which could be hacked. So as of right now, there is no security on that. It is still in development, but that is probably the only attack surface. Rob, if you have any more.
Yeah, so the motion server itself has parameters where you can input, let's say, password protection to access the server. So that's something that can be implemented into the configuration of the server. That's not something that we necessarily addressed at the moment, mainly because the server is only local. So you would need access to the Wi-Fi network in order to actually breach into the server. Otherwise, you have no access. So with a strong security on that Wi-Fi network, the risk is lowered, but obviously it's still there. It's present. Nothing's unhackable, but there are ways to kind of mitigate that.
And then also, I believe Russell had something to add on here too.
Yeah, just to address security concerns with the docking app, there's nothing that the app itself can do to read or write directly into the HoloLens without some sort of either password or credentials or certificates in the case of the HoloLens. Also with the docking app, the only security concern that's kind of remaining is I did not implement a OAuth authentication protocol on the actual login page. But I wanted to leave that open to be consistent with We Energy's security policies, which I was not aware of. And also, it would be a great opportunity to just sync that with their own database for login credentials.
All right, so the next question is, would the CSV file add the inspection data in the required fields in Cascade, or would there be additional manipulation of the data? So I'm gonna let Meg answer this. That's what she was primarily working with.
Yeah, there wouldn't be any additional manipulation to the data. It would all be like loaded into the correct spot. As of like right now, due to us not having access to like the laptop that WeEnergy's provided to us, we were unable to like completely like figure out what exactly forms we would need to submit. But like as like the demo showed, we'd be able to like load them directly into the correct place.
All right, so now our next question is, where's the QR code located for each substation? So the QR codes will be going on every individual device for inspection. That's how the inspectors will pull up the relative forms. And then in addition to that, I know this wasn't part of the question, but just something else that we can add on. Additionally, the RF tags for check-in will be located in a secure location outside the gate so that inspectors will scan that before entering the substation. Brendan, do you have anything to add with QR, or was that enough?
I think that was pretty good. So the whole point is it's just going to be recognition for each of the components. So you only need to scan that, and then you have the form for that exact piece pulled up right in front of your face for you to fill out. And there's no hassle with having to go and search for other forms.
All right, so our next question is, what amount of onboard memory, how much inspection data can it hold? So the system has a total of 4 different memory locations. The HoloLens has about 60 gigabytes of onboard memory, if I am recalling that number correctly. And we actually will primarily not be storing data on the HoloLens. Instead, one of the Raspberry Pis has a 120 gigabyte SSD drive, solid state drive, installed on it. And that is where we were planning on storing all data output and like the tag database, the QR database, device alerts, all of that. Currently, it does not do that simply because I had the SSD drive and couldn't connect it to the HoloLens because someone else had that component. But that is the plan for those pieces. All right. The next question is there a need to do camera calibration for accuracy each time the system is opened? Brendan and Rob, I believe you two will know more about this for IR and QR.
So the FLIR IR camera, at least the model that we're using, actually performs calibrations on its own. So there isn't a need to actually perform any calibrations for the camera itself, but you are able to manipulate the configuration file to edit, for example, resolution, frames of the actual screen. But for the actual calibration to detect heat temperatures, there isn't a need to calibrate. The camera does that for you.
Yeah, and for the QR code scanner, it's actually using the webcam that is already attached to the HoloLens, so that too does not need any calibration.
Awesome. So our next question is, what is the business benefits for implementing this system? So we believe that overall, this entire system will just help to completely streamline the inspection processes. It will automate a lot of it, including uploading data to Cascade, and inspectors will be able to talk or use voice to text to input data rather than having to type it out manually. Check-in will be faster. So we believe that the primary benefit for this system is that it will just reduce time both before, during, and after inspections. Do any other team members have anything to add on there? Okay. So our next question, will there be QR codes for equipment located in the substation control house? So yes, every piece of equipment that requires inspection will be equipped with a distinct QR code. equipment that shares the same inspection form will be using the same code, but each distinct piece of equipment will have its own.
Yeah, the point is to help automate the system so you don't have to go scroll through a list to go find the equipment you're looking at. The QR will just be scanned and then your report will just be generated immediately.
Yeah. All right, our next question is, can you please discuss some of the next steps needed to use this in the field? So the biggest issue that we had with this and the next steps required to use this in the field is that the 5 of us live in completely different parts of the country. And when the pandemic hit, we're all over the place and each of us have different pieces of the system. So in order to use this in the field, it's mostly just a project of integrating all of our already developed components into one complete system. For example, Unity, the application or the platform we were using to develop the primary application, will let users add new scenes, or let the developers add new scenes for each piece. There will need to be a new scene for the check-in system. There needs to be a new scene for device alerts and inspection recording, neither of which have been implemented yet. But we also believe those were a little more not as necessary to this system. But yeah, so the main thing that needs to happen is each component just needs to be connected together. In the project legacy document that Meg mentioned, we actually have a step-by-step guide of what our plan was to integrate the system and assemble it into one unit. And are there any more questions?
If there are no questions, I want to take a moment to actually recognize that this team did work really hard, and given the circumstances, they've actually done really a good job, at least in my opinion. I don't know if Paul or Dave would like to say something.
Definitely. If you can hear me, I definitely appreciate this team. This is Dave. Just their ability to keep after this and kind of develop some things that were just kind of rough ideas we had at the beginning and pursue things like the check-in and other pieces were nice. And I definitely thank them for their hard work and wish them luck.
This is Paul Gogan. I just want to second that. I understand that we're in a difficult situation, and always with senior projects, that last month of the year is always seem to get the most work done. And I appreciate all the support and the effort. And I think you guys really stepped it up a notch. We saw even early on in the year the work that you were doing, and it was a ratcheted up improvement from the previous team's work. And I guess just in general, I guess I'd like to have the team give their opinion on pursuing this further and what you think what the next if a next team would select this project, what do you think they could accomplish in another year?
So I can start that off. Yeah, so we definitely agreed. We believe this system or this project should be pursued in the future. We believe it's a very cool system and that it'll definitely help accomplish what it needs to. And like I was saying earlier, the main thing that needs to happen is just integrating all of the individual components together. So we believe that probably in another year, just one more iteration of a senior design project, this will be a realized product. Maybe not in its final state yet, but it will be all connected together into one single system.
To go off what Jeremy was saying, it's not just only integration within the system, though. It's also integration within We Energy's system. Just a lot of stuff is structured and kind of has a giant hole that needs to be filled with whatever data is coming from We Energies in terms of user credentials to work orders to all of the reports. It's just a lot of filling in all the gaps of the data.
So lastly, can you talk real quickly on your future plans for the team individually?
Yeah. So like our plans for after graduation?
Correct.
Okay. Well, I am planning on working at a law firm actually, but due to the pandemic, that has been pushed back. So we'll see what happens there.
I'm actually still looking for opportunities at the moment. I know that with the pandemic, a lot of them kind of closed off. So we're still in the process of looking on my end.
So I actually did 1 semester of co-op, so I have another semester of college left. But I have an internship that they want me to work part-time during the fall semester, and I'll most likely end up working there after I graduate.
I'm going to be working for a company called Capgemini as a data analyst consultant, and so that starts for me in June.
And I will be starting in July at IBM as a developer, which is hopefully it'll actually be in July.
And awesome. Well then, unless anyone has anything to add at this point, thank you all very much for coming to our presentation and listening. Also, thank you, We Energies, for this opportunity to work on this project. I believe I'm speaking for the whole team when I say this. This is by far the coolest thing any of us have ever done. None of us expected to come into senior design and develop an augmented reality application. It just seemed so crazy when we got this project that we sincerely want to thank everyone for letting us pursue this.
Yeah, to second that, it's been a really cool opportunity to be able to implement and design a system from like start to finish and an entire system, which I think is a really unique benefit of this project as a whole as well.
Yeah, I'm very happy that we've gotten this opportunity. I feel like each and every one of us had an awesome opportunity to grow and learn in different fields that have challenged what we had already known. And I think that was great, especially because some of us haven't had internships or haven't been able to work on a fully realized project. A lot of our projects just end with less than a semester of actual work. So this has been cool to live through and be able to have it from fall all the way up until now. We get to see every single progression of it.
And then just one last thing I'd like to add. I would also believe I'm speaking for the team when I say this. We'd also very much like to thank Dave and Paul for helping us with this project. Thank you so much for all the help. And then also thank you to Dr. Tama for helping us develop the system and keeping us on track.
You're very welcome from Dave, and agree. Thank Professor Tama and a little bit to DNVGL as well. I appreciate them kind of opening their doors and helping us give you guys a window into their software at least a little bit.
And also, let's not forget John Harvey, Rich Hilbert, and the substation personnel that helped out with that too.
Of course.
The people that actually do the work, you mean? I mean, not that I don't do work, but.
All right, wonderful. Well, once again, thank you everyone for coming. I'm going to stop the recording here. Have a wonderful weekend. Make sure you stay safe. Thank you again.
Best of luck in your future.
Thanks, guys.
Thank you very
Bye.
much.
Thank you.
Enjoy
Thank
the
you.
sun.